recap of what we talked about yesterday. So we saw that when we talk about privacy, it's not something that is a very scalar or binary quantity, and that's easy. It's either private or not private. It's very nuanced. It requires combining a lot of technologies together. It's not just about technologies and algorithms. It's also about regulation and policy. And so there's legal to it. There's all sorts of things. User interfaces, user experience, etc., etc. And so we saw this very complicated drawing where we said that there's three main axes. There's the data sources, there's the different kind of models that we might want to train and where they live and who they belong to. And then when we prompt and work with these models, how we access the models and what we feed into these models. And all of these three axes, they kind of play together, but they serve different purposes and different people. So protecting the privacy is very, very complicated. Then we talked about some principles, some guiding principles for us. We saw these 4 privacy principles. And we focused mostly on data minimization. We saw this example of if you wanted to learn popular items, you could, instead of shipping all the items to the cloud and centralizing this whole thing, building a histogram, grabbing the most frequent items and then throwing away the ones that are infrequent, you could, via federated analytics, interactively build the knowledge. And then you could essentially prevent the server from learning things that don't appear very frequently on device. We saw federated learning. We talked about cross-device. Again, this is the setting where you have many, many phones or tablets, and they interact through a server in order to train a model collectively. The other kind of federated learning is cross-silo. Here we have institutions or silos, so it's somewhat different. And we also talked about data minimization for cross-device and cross-silo FL. And so we said there's minimized data exposure, focused updates, immediate aggregation. We try to use some sort of MPC protocols to securely aggregate, prevent the server from seeing the individual updates, try to keep things as anonymous as possible. We try to do limited release to the engineer that's requesting the computation. And then finally, we only deploy the final snapshot of the model. We don't deploy the full trace of models or the iterates, and that helps in minimizing who sees what and reducing the surface of points. We saw federated averaging. That's the simplest algorithm for FL. So you do multiple SGD steps on device, you train locally on the local data sets, and then you send those updates, you average those updates, and that's how you get a new model, and then you repeat the process many times. We talk a lot about how many times do we need to repeat this process. We saw that we could generalize federated averaging. The 2 main components are the client optimizer and the server optimizer. These are the 2 really building blocks that we would need to tweak and improve. There's a lot of research in this space on how we can use adaptive optimizers and how we can take into account data heterogeneity, device heterogeneity, compute heterogeneity across the fleet of devices we're training. So there's many different client-side optimizers and server-side optimizers. And that's where we stopped, essentially. So today I wanted to briefly emphasize some of the important topics that we didn't touch on and we will not dive into. But maybe some of you are interested in those. Those are not specifically privacy-related, so a little orthogonal to this summer school, but could be interesting and could interact with privacy. So the first one is about improving efficiency and effectiveness. So this is how do we design better FL algorithms? So how do we personalize these algorithms to people? Maybe we're training one global model, and after we train that global model, we want to send it to the device and try to personalize that model to every individual, whether it's a company or a user. How do we do something like reinforcement learning? These foundation models today, one of their secret recipes is we end up using this reinforcement learning human feedback in the loop. And it's really, really, really powerful because you give the model some signal that, hey, you're doing well or you're not doing well, you're answering my question or not answering. It could be just binary signal, or sometimes if you've used, for instance, BARD, you could give it like this was factually incorrect, or this was offensive, or this was something, You could even type a brief answer to the question that it missed. And with all those signals that originate on the device, we could actually use reinforcement learning to improve the model very quickly. And it's somewhat unclear how to do these things with FL. So there's open areas for improvement here. We talked about how do we even federate these very large models. This is a big open question. They're getting very large, billions of parameters. What parts of the model should we ship to device? How do we distill these models into smaller models? We learn concepts on device, and then we pack it together and put it in the bigger model. So there's a lot that we can do. The other thing is about fairness and bias. Because we are going to naturally have some underrepresented groups in the population of devices. Say you're training in the US, but you don't have very many, let's say Middle Eastern people in the US. And that's almost always the case. And let's say that population uses their keyboard, the English keyboard, very differently from the American speakers, let's say. So how do you design a Google keyboard that caters to everybody's preferences and the way that all these people use it? So there's obviously going to be underrepresented groups. There's going to be people with slower devices that they won't be able to finish the computation, people that don't have good internet connectivity, so they cannot download these models as fast as they should, or upload them as fast as they should. So there's many different ways in which we could create this equilibrium in the training process itself. So we need to be careful about how we design the system and how do we make sure we incorporate all these signals. The other thing that a lot of you actually had mentioned yesterday to me is being robust against attacks. Now that we're training on device, this creates an opportunity for people to jailbreak their device, and they could potentially tamper with the code that's running, or they could start feeding the model wrong data, faulty data. You could insert things to make the model perform miserably. You can insert backdoors. We saw this in some of the talks by other speakers. And so all of these are interesting open questions, and we've made some progress. We know how to deal with a little bit of them, but we haven't fully solved and addressed all these concerns. We're not going to dive deep into them. I just want you to be aware of them. There's this paper that's, I think, almost 3 or 4 years old now, so it's been out for a while, but it's still very relevant. It talks about all the system challenges, the fairness challenges, robustness, security, even privacy, and others. So if you're interested in diving a bit more into some of these open questions and interesting avenues for research, I invite you to take a look at it. Again, probably needs a refresh at this point, but a lot of the problems there are still relevant today. So, but for today, I wanted to switch and talk about the third privacy principle. So, and this is going to be the focus of the 2 lectures for today. So this is about protecting individual privacy. A lot of times we refer to it as data anonymization because it's a term that, especially in Europe, GDPR, the word anonymization refers to individual privacy. But in our community, in our research community, anonymization has very specific meaning, which is stripping off attributes, removing pseudonyms that could identify people, but it's not necessarily individual privacy. So we've switched to this terminology, but here's what it is. So if you're computing things, whether it's a statistic or a model, you want that model itself, the parameters of the model, or the output of the computation, to not reveal much or anything ideal about an individual. So you want to learn about the population as much as possible, but you don't want to learn something unique about one single participant in that study, in that group. All right, so that's really the crux of what we're doing here. And so differential privacy, as you saw earlier in this summer school, is one of those tools that allow us to do data science and statistics and machine learning, to learn as much as possible about a large group, while only learning very little, ideally nothing, about one specific individual. So if you share preferences and traits with a large group, we want those preferences and traits to be encoded in the model we're trying to learn. But if you have something very unique to you that nobody else has, certain activities or certain preferences, we don't want those things to be strongly encoded in the model. Because then, we could look at that model and we could say, all right, I know that Peter actually does such and such. And that's very different from what everybody else does. So that's the idea of it. And the way we mechanically use it, and I think Jano talked about it, I will try to mention it again because I think it's important, is as follows. So let's say you have a data set D. You're trying to compute a query on this data set. For the sake of simplicity, let's assume you're trying to train a model on this data set for this lecture. So classically, we could apply any optimization algorithm, and I'm being agnostic on how this optimization algorithm is being applied. It could be done in a distributed fashion via federated learning. It could be done in the data center in the cloud. It could be done any way you like. All right. And again, it does not have to be just model training. It could be any type of a SQL query or any type of a statistic or aggregate. This is an arbitrary query. So now if you take a neighboring data set, and we'll talk about what does a neighboring data set mean. For now, think of these two data sets as identical except for maybe one record. Just one record that's different between these two. And you reapply that query, so you're going to get a new output. You have two data sets, D and D prime. You'll see outputs M on D and M on D prime. All right? Now, ideally, if I want privacy here, in some sense, I would hope that if I just change one record, the output of the computation is not going to change much. So if I look at M of D and M of D prime, they look a lot alike. Statistically, they would have distributions that are fairly indistinguishable, very close to one another. All right, so think about your favorite distance metric on distributions. You want the distance between these two distributions, the distribution over M of D and the distribution over M of D prime, to be very small. You want them to be very close to one another. So we can talk about a lot of distribution measures between outputs or distributions over outputs. And DP uses what's called max divergence or infinity divergence. That's a very specific kind of divergence. You may have seen it also under the name hockey stick divergence. So if you're an information theory kind of person or a stats kind of person, you may have seen max divergence or hockey stick divergence, and that's precisely what it's trying to do. So very briefly, what it's saying is that the distribution of M of D and M of D prime should be close in an epsilon delta sense. But these are the two parameters that control the distance between these two distributions. So delta here should be thought of as something extremely tiny. So think 10 to the negative 5, 10 to the negative 6, something that's kind of cryptographically small. So the smaller, the better. It's like some sort of a slack, and we'll talk a bit about what it means, because bad things can happen if delta is large. We don't want delta to be 0.1 or 0.5 or anything like that. We want it to be 10 to the negative 9 or 10 or something very small. And epsilon is essentially a multiplicative factor in terms of how much the ratio between these distributions can actually change. So that is something that we want to control as much as possible. And ideally, we want epsilon to be less than 1. For these two distributions, in theory at least, to be quite close to one another, we want this epsilon to be as close as possible to 1, preferably below 1. Obviously, achieving that is going to be very difficult. We're going to talk about it, but that's the ideal scenario if we could achieve it. And notice that it says that over all neighboring database pairs, over all output spaces, there's a lot of like worst case things here that's happening. So this criterion needs to be satisfied over a lot of like worst case things. And that's what makes the definition very strong. And we'll dive a little more into it, but that's the high level idea behind it. Now, one thing I've glossed over intentionally is the notion of this adjacency between these two data sets, D and D prime. I said they differ by one record, but I didn't even define what that record means or what it is. So technically, they should differ by one X unit in the training data. But we need to be very precise about what that X unit is. All right, so saying, this is differentially private without being very explicit about the unit of adjacency or the unit of privacy is, I would say, quite wrong. And I've seen a lot of papers that would just say this is differentially private. Kind of need to quantify the notion of differential privacy that you're using. So let's talk a bit about that. So one very popular notion of adjacency is called example level adjacency. You may have heard example level or item level. It appears under different names, but they all mean the same thing. And what that means is that if you take two data sets, these are two training sets and they're used for training language models. That's why you'll see in every row in the data set, you have a training example, and that training example is just a set of words. It's a phrase that we use for training some sort of a language model. You'll see that the only difference between D and D prime is just one training example. There's only one row in this data set that refers when we go from D to D prime. So this is called example level D. Because when we go from D to D prime, we're only changing one training example. It has a meaning. It just says that the model should not change much if we only change one training example. So it's meaningful in some sense. But the one that we prefer to use in practice, especially in the context of federated learning, is called user level DP. And notice what happened here. The first thing is I added a column, which is the user ID. So you can see that you have a bunch of users. This is, by the way, a Shakespeare data set. So these are characters from one of Shakespeare's plays. All right. And when I'm going from D to D prime, I'm changing all the records that belong to one user. So that's very important. It's not just one training example that's changing from D to D prime. It's all the training examples that belong to a single user can be swapped, can be arbitrarily changed when we go from one data set to the other. But you can see that this is much, much stronger than the previous definition. Because in example level DP, we can only change one row, whereas here we could change an arbitrary number of rows, all of which belong to one user. Okay? So achieving this is going to be harder, and we're going to talk about it as well. But these are the units, and there's other units. So there's nothing very special about example level or user level. It's actually a spectrum of units of privacy. And that's the thing that I want you to kind of take away from this part of the talk at least, which is you can start at the token level, which is not even a full example. It's just one word, one token in a training example. This is in the context of language models where you have a sequence of tokens that form one training example for a language model. You can go a little, larger in scope. You can talk about example level DP, which we just saw. You can talk about paragraph level DP, which is multiple training examples, or document level DP, and then all the documents that belong to a single user, that's user level DP. And then you can go even broader in the cross-silo setting. You can talk about organization level, which is even broader because every organization is going to have multiple user customers. So, but notice what's happening as we go down this list. Basically, it's getting exponentially stronger because that is going to dictate the unit of the epsilon, and the epsilon appears in the exponent of the definition. So we need to be a little careful because we might be shooting ourselves in the foot. Ideally, we want to strengthen the unit of privacy, but it's going to come at a higher and higher price. So that's just something for you to be aware of. And we like user level DP a lot in the cross-device setting because the basic unit in a cross-device FL is the device itself, which is owned by a user. We want to give the protection at the level of the user. It does not mean much to give the protection at the level of one training example. All right, so any questions on this? This is, I think, very important. Cool. All right, so now that we know what DP roughly is, at least the spirit of DP, what it's trying to do, let's talk about how we achieve DP. And this is where it gets a little dicey. So the next part of this talk is going to get a little, into the weeds of it. So bear with me. So there's this thing called the Gaussian mechanism. This is essentially the holy grail of DP. There are many other mechanisms that are just as important, but the Gaussian mechanism is arguably the most important mechanism in DP. So how does the Gaussian mechanism work? Let's start by scalar queries, so simple, very simple queries. So Q of D is the query we're computing on a data set. This is the query of interest. And for now, think of it as you ingest the data set and you compute a scalar quantity. So one-dimensional simple quantity. Okay? So what we're going to do here is we're going to take that quantity and we're going to add to it Gaussian noise. So it's a simple Gaussian noise with a standard deviation signal. As simple as that. So you can see it's very simple. So the mechanism releases the correct query output plus some Gaussian noise with a standard deviation of sigma. Now, technically this already achieves DP, but there's some subtleties that we need to talk about in order to understand what level of DP are we achieving and how we control that sigma. What does that sigma mean if we want to achieve some epsilon DP? So how do we set that sigma? And I'm not going to go into proofs, but I'm going to give you intuition and show you how to do it. So first, we need to talk about the sensitivity of the query that we're trying to compute. This is an important notion in DP. You may have heard a lot of people talk about sensitivity of queries. So this is essentially if I take two adjacent or neighboring data sets, again, we just talked about what are these adjacent data sets, pick your unit of privacy, let's say user level. You can change all the records that belong to one user when you go from D to D prime, and you can do it arbitrarily. So you can consider arbitrarily a pair of neighboring data sets and take the difference between the query outputs on D and D prime. So I just want to see, if I change one user, in a worst case sense, how much can this query output change? It's really a sensitivity analysis. You may have seen this in even math classes where you do like the sensitivity of a function. That's independent of privacy, but in privacy it takes on a very specific meaning. All right, so you just look at how much can the query output change if I change one user, let's say, or one example in the data set, and you compute the worst case change in the query output. All right, let's call this the sensitivity of Q. It turns out that we can take an example here. Let's say Q is a simple count query. So I'm counting the number of people that are above the age of 65, right? So if I change one person in the data set, in the worst case scenario, what can happen here? Maybe one person was above 65, and if I swap that person with someone else, I would swap that person with someone who's below 65. So the best that can happen is that the query output would change by 1, right? The count is going to differ by 1. It's a simple count query. So this function is very well behaved. It has a sensitivity, a max sensitivity of 1. There are functions or queries that are not as well behaved, and we're going to see some examples of them on the next slide. But let's focus on this one. Now that we know the sensitivity, if we would like to target an epsilon, a specific epsilon, what we should do is we should set the noise to be the sensitivity divided by epsilon. And this has a very intuitive meaning if you think about it. So the way I'd like to think of it is essentially, if you want to find how much noise you have to add, it has to be calibrated to the sensitivity of the query. So queries that have very high sensitivity, you need to add a lot of noise to it. So in this specific example, because the sensitivity is 1, we're only going to add something 1 over the privacy level we want. Smaller epsilon means more private. We need to add more noise, and that makes a lot of sense, right? So if we go from epsilon equals 1 to epsilon equals 0.1, that's more privacy, and we need to increase the sigma. We need to add more noise to achieve that EP level. But if we go from a query that has low sensitivity, such as 1, to a query that has very high sensitivity, such as 10 or 100 or something even worse, we need to add more noise. Sigma scales proportionally to the sensitivity. All right, so this is very basic and very simple, but I want you to be 100% sure that you got this. There's a proof for why sigma should be precisely set as follows. We can go into the definition of DP and do some math with Gaussian distributions and try to prove that this specific choice of sigma indeed satisfies that definition, but I'm not going to do that for now, okay? So we can move on to something a little more exciting, which is what if these queries are multidimensional? And this is one step closer to machine learning. Because in machine learning, we're training models, and models have many parameters, not just a single parameter, right? And so we can view models as vectors in some d-dimensional space. And therefore, we need to talk about this multidimensional query, if you want, settings. So what would change here? The notion of sensitivity would change. These queries are not scalars anymore. They output d-dimensional vectors. So we need to look at the worst case change between any two neighboring data sets. The notion of neighborhood between data sets is still the same. You still change the records belonging to a single user, and you look at Q versus Q of D, the worst case change in the output of the query. But those outputs are not scalars anymore, they're vectors. So the way we measure the difference is via an L2 model. So instead of taking just the absolute difference as a scalar quantity, now we take it as L2 in an L2 sense. That's how sensitivity is defined. And we call this the L2 sensitivity. There are other mechanisms, such as Laplace, you may have seen it or heard of it, the Laplace mechanism. They require controlling L1 sensitivity as opposed to L2 sensitivity. But for the Gaussian mechanism, we need to really control the L2 sensitivity. Okay? And still the same. Once we have that sensitivity, we choose sigma to be sensitivity divided by epsilon. And notice now, the noise is not scalar. The noise is a multidimensional Gaussian vector, but it's IID across coordinates. So it's still sigma standard deviation per coordinate. Okay? Very simple. But let's take these two examples. So suppose this query now is still a count query, but instead of a single count query, now we're doing D counts. Our query is counting D different things. For instance, let's say we're counting number of females, number of children, number of people with COVID-19, etc., etc. You can see that if I go from one data set to the other, if I change one person, I could change a person across all these attributes. So I can go from a male to female. I can go from a child to an adult. I can go from someone who has COVID-19 to someone who does not have COVID-19. That change from D to D prime, I could arbitrarily change all the features when I go from one person to the other. And therefore, if you compute the L2 sensitivity of this query, it's going to be root D, because I can change all the D features here. So if I take the difference between Q of D and Q of D prime, I will get a bunch of ones on all D coordinates. And therefore, the L2 sensitivity would be root D. This is an example of a very bad query. By that, I mean a query that is hard to privatize, because we need to add a lot of noise to privatize it. So when you set the sigma, there's that sensitivity term in the numerator, and you're going to have to set that term to be something that scales with root D. And so if D is large, you're going to have to add a lot of things. And that's just not ideal, right? Because you're going to have to introduce a lot of error into the computation. Now, one could actually look at queries that are well-behaved, essentially. They have small sensitivity. For instance, if I compute, again, a D-dimensional query, but this query is the number of people between 0 and 4 versus 5 and 9 versus 10 and 14 versus 15 and 19, so on and so forth, right? So now if I change one user between D and D prime, what can happen is that most, you can have somebody fall in one of these age groups, move from one age group to the other. But you will not essentially change on all the buckets and all the age groups by swapping only one user for doing user level. And because of that, if you compute the sensitivity of this query, it's going to be root 2. Essentially, you have two buckets that would change from one query to the other. Let's say someone was in the age group 5 and 9. When I swap that person, I'll swap them to, let's say, 10 to 14. So the difference between Q of D and Q of D prime is only in these two entries. And that's why it's root 2 in L2 sets. This is very well behaved, because no matter how many age groups you have, the noise is not scaling with the number of age groups that you have. D, the dimensionality, is irrelevant here. You're going to add constant noise.
Why is the sensitivity in the last example, in the well-behaved query, dependent on the size of age groups? Because one would say that if I have very narrow age groups, 0 to 1, 2 to 3, that it's less private than 0 to 10, 11 to 20, right? Because you aggregate more, let's say.
Yeah. So
wouldn't it be dependent on that?
Sorry, can you repeat the first part of the question?
Why is, in the last case, the sensitivity not dependent on the sizes of the groups in this case? Because if you aggregate over more, you get more privacy, intuitively, I would say.
Yeah. So this is a very good question. I did something here to mostly highlight how bad sensitivity versus good sensitivity works. But there's a caveat that I actually intentionally hid from you, which is that if your objective is to get very fine-grained information, right? If you start dividing age groups into very fine, buckets, like ages 0 to 1, 1 to 2, 2 to 3, and so on and so forth, you're going to get less and less people in every bucket, right? When you aggregate over larger buckets, you're going to get a stronger signal relative to the noise you're adding. Whereas, sure, even though it's still root 2 sensitivity, it's still the same amount of noise that I'm adding, but I'm getting weaker and weaker signals. So I'm still encouraged, even in this case, to group people into as large of buckets as possible so that when I aggregate, I get the largest signal relative to the noise.
Okay.
So it's a signal to noise ratio kind of analysis. But in this situation, I'm just focusing on sensitivity, not the accuracy of the computation. Just to demonstrate the concept.
What if our sensitivity cannot be bounded? For example, our query is an average of earnings, and we, of course, can swap any people to Elon Musk and get some infinite earnings.
Yeah. Yeah. So there are queries that are that have unbounded sensitivity, and actually, when we talk about models, we're going to see this in maybe 5 slides or something like that. When I'm training, I get these model updates. I don't have control over the L2 norm of these model updates. In theory, they can be arbitrarily different. So what we do in this case is we explicitly bound the norm of these vectors. And this is something I'll talk about it, very carefully because it's very important. So in cases where the sensitivity is unbounded, we need to figure out a way of how we can deal with unbounded sensitivity, and usually we clip it. We try to control the L2 norm of these things. So we'll see an example in the context of that now.
Okay, great, thanks.
That's very good. Any other question? All right, okay. So this is the most important slide because this is the one that allows us to do provable differentially private machine learning. So this is the one that Jan talked about. I'm going to go over it again because I think it's very important, and I'll emphasize slightly different points. There are some properties that make DP extremely useful in practice, and there are roughly 4 such properties. There's more depending on who you talk to, but the ones that I care about the most are the following 4 properties. The first one is the easiest one to understand, which is called the post-processing property of DP. And what it vaguely means at a very high level, it says that if I compute a differentially private query, whatever that query is, I take the output of that DP query and I post-process it. Post-process it however you want, in a deterministic, in a random fashion, apply any function you want on it, as long as that processing does not touch the data set. As long as you're not bringing in the data set again, right? So put the data set aside, take the output of the query that you computed with DP and compute whatever you want on it. That will still satisfy DP. And it's intuitive, right? If I already privatize something and I put it out in the wild and people take that something and they compute whatever they want on it, we're not going to suddenly unprivatize it. That's just well-behavedness.
What about things like denoising models such as autoencoder? What about cases such as denoising models like denoising autoencoders? Would it count as cheating because you bring in the data, or
no? So that's important. If the denoising step is done without touching the training set, so you're doing some sort of filtering or projection. I know something about the application, and therefore I know these values need to be bounded between 0 and 1 or between whatever, 0 and 10. If you do that without accessing the training set itself, then your post-processing will not violate DP. You will continue to actually have a differentially private path. If you go and access the data sets, and learn something from the data set, and from that thing you do the processing itself, then you're violating this property. So that's something we need to be very, very clear about. The post-processing preserves BP, but that post-processing needs to be done in a way that does not access the data set. As long as you're not touching the data set, any post-processing you perform is going to preserve the DP property. Okay? Yeah. So that's the first one. The second one is arguably the most important one here. It's called composition. And this is something Emiliano talked about, which is if we have one data set, and instead of computing one query on this data set, we compute many queries. This is very relevant for machine learning, because in machine learning, we compute multiple gradients, and we do many batches. We're touching the same data set many, many times, right? We iterate, and we do thousands, hundreds of thousands these days, every time touching the data set a little bit, all right? So if every one such operation or computation or query is differentially private, can we argue about the privacy of all those queries simultaneously? If I look at the trace of queries, each one of them is differentially private. What can I say about the collective, trace of queries? You can see that this is important because I'm looking at each one of them, what happens to all of them. And DP has this very nice property. It says that the privacy loss degrades very gracefully. This is a topic that took years for us to develop and understand. And until now, there's more research that's done on how we can do tight composition. We want to basically bound the privacy loss over many such queries. I'm not going to go into the latest and greatest of these, we call them privacy accountants. But the idea here is that we now have tools that are very developed that allow us to talk about the privacy leakage of many queries on the same database. And it turns out that DP has a very graceful degradation of privacy when we touch the data set more and more. It's not even linear in the data set, in the number of times we access the data set, it's sublinear in the number of times we access the data set. And that's actually what allows us to train models very efficiently. Right? Again, I'm not going to go into details. I'm happy offline because I wanted to emphasize other things in this lecture. But the idea is that this one is sometimes very helpful to use. It's not very widely used. It's called group privacy, but it actually can be very helpful. So let me try to explain this to you. So you fix a unit of privacy. Let's say user level DP. We're saying if we swap one user by another arbitrary user, we have the privacy protection of DP. But what happens if you swap k users? So let's say I suspect that there's 5 individuals in the data set that have very similar statistics, right? Let's say they're, siblings or part of a family, and they share the same preferences, or they do the same activities, or they communicate together, so their messages are strongly correlated, so on and so forth. It could be a person and their partner and children or whatever it is. You can think of it in any context you want. If I'm exchanging emails with people, there's always a sender and a receiver, so it's not just swapping one person, maybe 2 people or something. All right? What this tells us is that even if we focus on a unit of privacy of, say, 1 user, if we now change, instead of 1 user, we change k users, privacy again degrades very gracefully. This time it degrades linearly in the number of such users we're swapping. So this is a very interesting, subtle difference between composition and group privacy. In composition, I said it degrades sublinearly in the number of queries. So if I do k queries, the way epsilon will get weaker is root k. That's sublinear in the number of query accesses. Whereas in group privacy, it will degrade linear in the number of users that I swap. So if it's k users that I swap, epsilon will get weaker by a factor of k. And there's no way around it. We tried a lot to see if we can tighten this. It turns out that it's fundamental. If you want to swap k individuals, you're going to be bounded by that factor of k in terms of how much weaker the epsilon is going to get. Okay? The last one is, again, one that's very, very important for machine learning. It's called privacy amplification by Dziembowski. And so this is arguably the hardest one to understand or to intuitively explain, so I'll do my best. So what it says is that if you have a data set And if you compute that query on the data set, on the full data set, and we can prove that the output of the query is epsilon differentially private. Let's say I'm applying the Gaussian mechanism, I control the sensitivity and the standard deviation to get epsilon dp. Okay? Now, what happens if instead of computing the query on the full data set, I do the following. First, I subsample the data set. So I go over the queries of the data set, over the records of the data set, and each record I select it with probability Q. So I have a data set, let's say it has n rows. I will go over every row. Every row I will flip a biased coin. With probability Q, I will keep the row. And with probability 1 minus Q, I'll throw the row away. So I'll end up getting, obviously, a smaller data set. Arguably a much smaller data set, depending on the value of Q. So let's say Q is 0.1. So 10% chance of keeping every row. So I'll end up with 0.1 times n rows. The original data set has n rows. So much smaller data set. Now, if I hide that small data set from the adversary, so the adversary will not know which rows were selected versus which rows were thrown away. Me, as the person who's computing the query, I would know which rows I've selected, but the adversary does not know that sample. But now I apply the same mechanism that achieves epsilon dp on the original data set. I apply it to the sample data set. What this principle is telling us is that if you do that, you get a boost in privacy. And it's very intuitive. The reason why you get a boost in privacy is because now the adversary not only has to fight the noise that you're adding into the output of the query, which was calibrated to the original data set, the adversary has now to guess which rows you've selected. So there's two parts of randomness that are kicking in. There's the randomness that comes from sampling those records that's going to add confusion to the adversary. The adversary now will have to loop over many possibilities. Did Peter select the following rows versus that other set of rows? So there's a lot of confusion and randomness that comes in. And then the adversary has to fight that Gaussian noise that you added. And therefore, the net effect would be a boost in the privacy. So what happens to the epsilon, after you perform that subsampling step, it gets amplified by a factor of Q. Notice something here. I say amplified, but what that really means is that it gets reduced by a factor of Q. Because smaller epsilons are stronger. So Q is a factor less than 1. It's the sampling probability. Let's say, again, I sample with probability 0.1. I get roughly a 10x boost in privacy. Because my new epsilon is 0.1 the old epsilon. The epsilon that I computed on the full base.
Cost? Queries will also get worse.
No, there is a cost here. That's a very good point. The cost is that now I have a lot less rows to compute that query on. So the signal is also getting weaker, right? So because I don't have the n rows, I have 0.1 n rows, the signal is getting weaker. But here's the thing. If I'm doing optimization, we anyway don't compute the gradients on the full data sets, right? We use something like mini batch SGD. And in the limit, we use stochastic gradient descent, where it's only one record. So naturally, we already are doing that step. We already are selecting a subset of the training examples and computing the update per iteration on only a small slice. We never compute it on everything because we don't have to compute resources to compute the gradient on all the training examples. So essentially, we get this in machine learning technique.
Sorry, I have a question. What about the second security parameter, namely delta? Is it changed, or we have any control over this?
Yeah, we have control over it. By the way, I'm hiding deltas in all these slides because they're slightly irrelevant, but we have control over delta, and it's a very nice way to control delta. I don't want to confuse and make the slides very complicated.
One question. So, in the basic definition of DP, like you have neighboring sets, so it can be somehow, like in my mind, it's very strongly understated what D to D delta can be. If we know something about the population and say, like, the high probability everybody is actually going to be in some range or something. Can we do better, like by relaxing the definition of measurable?
Can you elaborate a bit more on?
I'm just thinking like if somebody, so our sensitivity increases depending upon how we define the neighborhood.
Yeah.
So it's a very strong definition. So if with high probability you're actually going to be much closer and the attributes are not going to be different, can we do better? I mean, there is a loss of privacy, but like this to me is like a very strong definition, which is useful to protect minorities.
Yeah. I mean, we have relaxed notions of DP, some of which take that into account. The most popular one is called geo-indistinguishability in the context of location. And in context of basically location traces, we take that into account. Into the notion that basically the epsilon itself would depend on the neighborhood. So I'm not going to go into these more advanced concepts. I'm going to keep it simple. Yeah. All right, so these are the 4 properties, and honestly, this is the most important slide. But I want you to understand these properties because we're going to put them together in a bit to do ML, and we're going to need practically all of them except for group privacy. That's the only one I will not use. But post-processing, composition, and privacy amplification are going to be the 3 critical ones. So if you have any questions on these, or if you didn't understand them, I'm happy to repeat, use the board, scribble, go slow as much as possible.
Is the last point?
Yeah.
The 4th point, like something like membership inference, but without knowing the sample. So I want to know if my unknown person I'm looking for, but I don't know him or his their personal information, which I want to find out. I don't know if this person is in the data set that was actually used to compute this average that I have right here.
Yeah. So that's a very good question. Actually, you can think of these all connected to membership inference, and I'll get to it in hopefully the second lecture today. The connection between DP and membership inference, the equivalence between them, and how these concepts actually play into like practical attacks. So I'll defer the answer to the next lecture. Okay, so let's keep going and let's look at how we can put these concepts together quickly to do ML with. And for now, again, I'm going to ignore federated learning and I'll come back to it in 5 minutes. But let's think, we have the data set centrally and we're computing a model in the data set. So this is how it works. It's actually quite simple. We're going to first sample a batch. This is a mini batch. We already kind of do that when we train ML models. There's a slight difference between how we train ML models and this step. For ML models, if you've any experience with training ML models, we take the data sets, we shuffle it, and then we go in disjoint batches. We do one pass, often called epoch. We can do it again and again and again. We can do multi-epochs or multiple passes. We take the full training set, we shuffle it, and that shuffling itself is also introducing some sort of randomness in the order in which we're ingesting these training examples. But for DP purposes, we're doing something similar but not exactly the same. Instead of shuffling the training set, we're sampling the records in an IID fashion from that training. Okay, so there's a sampling uniformly at random of training examples. Okay? And we first compute the gradient on every training example for the gradient of the loss of the model. That's exactly what we do in the mini batch FGD. And there was a question about sensitivity. What if these things have unbounded sensitivity? And indeed, if you look at the gradients of the loss in typical ML application, it might have an arbitrary L2 norm. In reality, it will not, but in theory, we don't have a way to say its L2 norm is going to be strictly bounded by whatever. And so we apply this clipping operation. We clip the L2 norm of every gradient to S to make sure that the sensitivity of this query is going to be bounded to S. So this clipping operation is just a way for us to control the sensitivity. And notice that S should not itself be set as a function of the data set. We have to pick a number and delete it. Let's say pick a norm of 1 or a norm of 0.1. And just say, all right, I think that my gradients are all going to have a norm below 1 or below 0.1. Or the majority of the gradients are going to have a norm below 0.1. Okay? We'll talk how to set it in a bit. Then we will compute the average. That's very similar to how we do mini-batch SGP. We compute those gradients and we average them. The only difference so far is that we've clipped the gradients to have bounded L2 norm. And after we average them, we add the Gaussian noise. Now that we have bounded sensitivity, and that sensitivity is S, we can have Gaussian noise with a sigma that's proportional to sensitivity divided by the epsilon we want to achieve in this axis, in this round. And we get a noisy gradient update. And if you understood this, I think we're done, because that's really all what DPML is about. It's about clipping those gradients to bound the sensitivity of the query. It's a simple query, it's an average query or a sum query. And then, we add the Gaussian noise as we discussed before. Literally by bounding the sensitivity and controlling to the level of privacy that we would like to achieve in this one round. Now all we have to do is just apply it again and again and again. If you want to train a model for, 100,000 rounds, you do the exact same step 100,000 times. And these are 100,000 queries on the same database, so we use composition to track privacy. There's one thing that I didn't emphasize here, which is the sampling step. The first step was to sample those records uniformly at random. That's going to boost your privacy. We talked about privacy amplification via sampling, and that's going to give us that nice boost in the privacy level. So that's how all these concepts actually kick in together. And because we keep on doing this again and again, we're post-processing already differentially private updates. So we're not breaking the DP promise.
So you're not adding noise to each of the gradients. You're just you're making the gradients all the same.
I'm averaging the clipped gradients. When I get the average clipped gradient, I add noise to that. So this is only like one application of noise per training round.
Oh.
Yeah, we'll talk about other variants. For now, I'm keeping it simple.
Thank you.
Okay. All right. Yes, there's exactly this question.
So in this notation from before, the query is like everything until the average, and then the mechanism is the average plus the noise. Right?
Exactly.
And then
and we did this clipping. We did this clipping because
that's part
without
of
that clipping,
query.
The query I would have not been able to control its sensitivity. So I did that clipping just to make sure I have bounded sensitivity query, so that when I have the noise, I know how to calibrate the standard deviation of the noise. But yeah, it's a simple average query. Turns out ML is simply doing averages.
And then the SGD step at the end is like this post-processing.
It's a post-processing, exactly.
But doesn't it depend on the previous model, and that depends on the data?
Yeah, but every time, so you start from a randomly initialized model, let's say. So start the model parameters from some random initialization. So the first time you compute this thing, it's already DP. And you're going to post-process it by updating the randomly initialized model, right? So now you have something that's already DP. I'll compute a new thing with DP, right? And I'll take the DP thing and the other DP thing and I'll put them together. That's just composition.
Okay.
So I'll put these things together and apply composition as I go to compute the overall privacy budget of this object.
Mm-hmm.
So I have a question about what changes as you add more data. So let's imagine that you have two data sets, the second one twice as big as the first one,
yes.
And you want to train on both data sets for one epoch. Yeah. So the second training will take twice as many runs because you use the same path size.
Yes.
Then you use this second training, you will get twice as bad epsilon parameter at the end, right?
Yeah.
So you use more users, but your security guarantee is twice or
So there's a caveat in what you're saying, which is you're able to run twice as many rounds.
Yes.
And being able to run twice as many rounds means you're able to converge to a better point. There's another way actually to do it. I would not advise you to do it the way you explained it, which is instead of doing twice as many rounds and paying the price in the epsilon and hoping that you converge to a better local optimum, I would say what you should do is you should grow the size of one round. So instead of, let's say, in the original data set, you're sampling 1,000 training examples, now sample 2,000. Because the sampling probability is going to be fixed, right? When I go from D to the other data set that's twice as large, I could sample twice as many examples and keep Q fixed.
Yes.
So now you can do the same amount of training rounds with the same Q, with the same noise, and therefore the same epsilon, but every round is going to see twice as many examples. And therefore, in every round, you're going to get a better estimate of the per round gradient. So definitely, you're going to converge to something better.
Yeah, so this average gradient is better, but you are still adding the same Gaussian noise on top of it.
No. So okay, so that's something that again I'm at fault with it. When you average, the sensitivity here isn't S. The sensitivity here is S divided by the size of the batch. So if it were a sum, not an average, changing one of these gradients would change the sensitivity by S. But because I'm doing an average operation, if I change only one gradient, how much can the average change by? So the query here is the average thing. It's going to be S divided by the batch size. So that's important to keep in mind. So if you grow the batch size by a factor of 2, the sensitivity here is going to be halved, and therefore I would add less.
Okay.
Isn't it also the case that if we are increasing the size of the data set by a factor of 2, we are in the first scenario sampling less samples, as taking into account the ratio of the samples to the size of the data set, and therefore even if we are training exactly the same number of epochs, we still should get the same guarantees?
I think the question, the way I understand it, is that the adversary knows if you're using the first data set versus the second data set. So in this question, if I were to use the larger data set, naturally the adversary knows that you have twice as many users, and there's twice as many people for the adversary to try to kind of decide who's in and who's out from. And so it's basically just a very natural property that says that if you have more people, you can get privacy for cheaper, more easy.
Okay, fine.
Did I address your concern, or did I confuse you?
Yes. Thank you very much.
I did.
So basically, there is a trade-off. If I could continue, you have fixed data set and you have to choose the bar size.
Yeah.
So you could choose smaller bar size and more rounds, and how this affects your final privacy.
Yeah, so that's a very good point. So let me see if I could try to summarize it. I should have had a slide on essentially these trade-offs. So thanks for the question. Technically, my tip for you would be the larger the batch, the better. So if you could, in theory, compute the gradient on all the training sets, I would advocate you do that. The problem, however, is that this is computationally very expensive. For DP, the best thing that you can do is actually take all the training examples, forget about amplification via sampling. I'm not going to get any amplification via sampling, but because when I average over all the training examples of the data set, the sensitivity per iteration is going to be very low. And that is the ultimate best thing you could do, but computationally it's very expensive. So then what we do is we actually walk backwards. We say, assume I have some amount of computations. So let's say, for instance, I can compute only 10,000 gradients per update. Now I can say, all right, if the data set is of size blah, what's the amplification that I get from sampling, and I work it out.
That's it.
Okay. And we're going to touch a little more on it in slightly different functions.
This may be going a little bit too deep into details, but there is something like gradient averaging, when you average over multiple batches and then you update the weights. And what about the privacy of that technique? Can we technically cheat to make it update on the whole data set using?
Can you elaborate a bit more? I'm not sure. So what do you want to do exactly?
Just accumulate the gradient over multiple batches and then do the update. And would it be like more private or?
Yeah, so it depends on what you release to the adversary. If I could, instead of updating the model, do many small, let's say, mini batches. Let's say instead of one mini batch, I'll do 10 mini batches while keeping the model parameters frozen. And then I average all those 10 mini batches and make one DP update to the model. But I can ensure that all those 10 mini batches are kept hidden from the adversary, then that's going to help. Because effectively what it's doing is it's actually 10xing the size of the batch.
Mm-hmm.
So it's allowing you eventually to average the noise by a factor of 10. But the devil is in the details. If you're actually releasing the outputs of every mini batch, then you have to account for that. The adversary already saw something that you computed on those smaller mini batches. So you can do it only if you control for what you release. That update, the model update, has to be done only after 10 mini batches, and all the intermediate information has to be kept hidden. So that's something you need to do.
Yes, you can say that larger and more expensive GPUs are more private.
Yeah.
I think there is one more threshold if I look at it technically, because I was thinking about it. So the initialization of the model, like the initial weight initialization, is very critical because the clipping can stop me from jumping to the right direction fast, so it will be slower. And please correct me if I'm wrong. And the no edit noise does pretty much the same. So convergence in this case, as far as I understand it, would be slower than if I would remove the differential privacy techniques.
Definitely, but actually I want to expand on what you said, because clipping and noise are not the same. So let's take noise without clipping first. You're still getting some sort of an unbiased estimate of the per batch gradient, the per mini batch gradient. Mm-hmm. It's just a noisier estimate of that gradient, but still unbiased. Yes. On average, it's still the same exact value that you wish to compute. So with just noise, you're still going to converge. If you have a convex smooth loss, take your favorite result on optimization, that is still going to apply. It's just going to converge slower because the variance is now bigger.
Because it's zero mean. Because it's zero
mean.
Yes. Yeah.
Now, that's the effect of noise.
Mm-hmm.
Noise is just going to slow down convergence,
mm-hmm.
right? So you need maybe more training rounds to converge, so on and so forth. Mm-hmm. Clipping, on the other hand, is an operation that could bias, that could introduce bias into the optimization. Mm-hmm. Why? Because clipping, it's not a zero mean operation.
Mm-hmm.
I'm literally changing the properties of the gradients. I'm
mm-hmm.
bounding certain things and clipping, some stuff. And so it introduces bias. So some people have reported, and there's beautiful research, up until maybe last week, I saw papers at ICML, where they analyzed the convergence of optimization under this clipping operation, and they can show that under some cases, you don't converge to a local optimum. Mm-hmm. You don't, even if you have convergence to global optimum under convex smooth losses, with clipping, you can construct under which you just don't converge at all. Mm-hmm. So you have to be careful about how you set the clipper.
Yeah.
Luckily, we don't see these things, these effects in practice, but in fact, in practice, clipping ends up acting a bit as a regularizer, so that's a separate thing.
Okay. Thank you.
All right, there's one other question there.
Yeah, just this one question. How much, this scheme is well analyzed theoretically in terms of, do we have settled, do we know exactly that, the epsilon is now optimal with an additional factor of square root of k, and what is the best choice of S, and what's the convergence rate, and all these standard settings?
Yeah, so if you take clipping outside picture, if you assume these gradients are Lipschitz, meaning they have L2 bounded norms, then we kind of fully understand the fact of DP and how to set the parameters and what are the optimal convergence rates, lower bounds, matching upper bounds, etc., etc. Very long, very rich literature in convex optimization and plus DP literature. Now, if you introduce clipping into it, it actually is like a nonlinearity in some sense. So the analysis gets very difficult, and there's now a growing body of research that tries to actually analyze either clipping separately or clipping plus what happens. And there's some, interesting worst case pathological kind of studies. One more question on the back, and then we can keep going.
Is there any privacy amplification if we assume, for example, the adversary does not observe the intermediate states of the model?
That's a very good question. Actually, in practice, we do observe that. And this is going to hopefully appear in the last lecture, where I'll talk about these membership inference attacks. It depends when you perform these attacks. If you show the adversary all the model iterates, that's something. You can estimate some epsilons. Jan talked a little bit about it. Jan talked about it. But if you hide the intermediate models from the adversary, you show the adversary only the final model, it turns out the epsilon is much better. So in theory, yes, there is a gain. We just don't know how to compute it. So mathematically, it's very difficult. We can compute it for very special cases, for convex smooth losses, but we almost never have those situations. We train deep neural networks, and those don't satisfy the properties that we need for the math. So the short answer is yes, you're right. The long answer is we don't know how to benefit from it, except for maybe measuring it and estimating it in practice, and we'll talk about it. That's a very good. All right, let's keep going, and we can talk more often. So everything I talked about was basically example level, because I said sample training examples in the first step. If you wanted to do user level, the one thing you would have to change here is that instead of sampling independent training examples from the data set, you would have to sample users. So you take the data set, you would group it by users first. So all the training examples of Peter are, grouped together, and for every other person you do the same. And now you go over users and you sample every user uniformly at random. So notice here, instead of R for records, I have U for users. So I'm sampling users and I'm computing the gradient on all the records that belong to a user. And then I average those gradients together and I clip the per user gradient. That's it. So it's still exactly the same, but instead of per example gradient, it's per user gradient. So I'm applying the DP at the user level, not at the example. All right, so that's just a simple extension to get user level DP versus example level. All right, so let's take a look at how we can do it in the context of federated learning. Remember this vanilla federated averaging. So here we have a device, and every device computes those multiple SGB steps locally, and we aggregate them. We get one model update, we send it back to the server. So how do we add DP here? So it's simple. Basically, exactly what we just saw. Before we send the update to the server, we flip it. Again, we flip it to bound the user contribution, to bound the sensitivity of the query. And now we do a simple average. We don't do any weighted averaging. Some federated averaging algorithms weight those users by the number of training examples that they have. We don't do that anymore. We just do simple uniform weighting when we compute the average. We let the server add that Gaussian. So this picture is very similar to the one that I just showed you here. These two are almost exactly the same. The main difference is what's happening where. In this one, it's all happening in the data center. It's an algorithm running in the data center, operating on the data set that I have acquired. In this one, it's physically happening in a distributed fashion. That clipping operation is happening on device, and those computations are happening simultaneously across the fleet of devices. But the noise addition is still happening on this. So this is called DP FedApp. This is where it gets really interesting. Because one, we need to control the clipping. That's something somebody asked me a question on. And this is where it gets interesting, because if I set that clip norm to be very small, then that's good for a sigma, right? Because it says that the sensitivity is going to be variable. If I if I clip to something very small, that S quantity is very small, the sigma is proportional to sensitivity, and sensitivity is exactly that clip norm that I apply. But I introduce a lot of bias because now all these gradients are being clipped, and that can introduce bias into my computation. Whereas if I set that clip norm to something very large, now I get rid of bias because no gradients are going to get clipped, which is great. But now I have to add a lot of noise because, again, the sigma of the Gaussian has to be proportional to sensitivity, and now sensitivity is very large. So there's this bias variance trade-off in DP, and it's actually fundamental. There's research on trying to break that trade-off between bias and variance, and there's no way around it. So can one of you tell me what should I do here? Someone who hasn't seen the stock. How do I set the clip in practice? How can I do it?
Maybe you do some pre-estimate, some kind of outlier and pre-outlier analysis, like initial exploration, and then you know at least the magnitude.
You know something about the distribution of the norms of gradients.
Yeah.
So and you set the clip norm based on that. That's actually a very good point, but there's something missing in what you said, which is that analysis that you have to do has to be done in the differential private.
Mm-hmm.
But if I do that analysis without DP, I'm violating the DP guarantee. Because I'm touching the data set, right? So either I use some proxy data, either I take one of the public data sets that I have that I don't want to satisfy DP for, and I try to use that data set, that proxy public data that I have, to come up with a good estimate of the distribution of the norms of gradients, and I set the clip norm to trade off bias and variance, or I do it on the actual data set, but I need to do it with DP.
Or blow it on the fly, like it did too much, and not use it. So we only clip line outside of per sigma.
Yes, that's exactly what I was going to present. So there is a strategy that my teammates at Google came up with called adaptive clipping, where on the fly you adjust the clip norm. So during training, we're not going to use a fixed parameter S for clipping. We're going to start with some random guess. Let's say I set it to 1. And then when I set it to 1, I will see how many gradients were clipped per round. If it's a lot of gradients being clipped, it means that I'm being very aggressive on the clipping. I need to reduce my clip. Or in other words, I need to actually grow that S. I need to clip less gradients, right? And vice versa. I notice that no gradients are being clipped, it means I can clip more aggressive. And as I go, I continue to adapt S so that on average, I only get 50%, about 50% of the gradients clipped. So I clip to the median norm. And this needs to be done with DP. Basically, this adaptation of the clip norm needs to be done in a differential private. So you can think of it as an adjacent query I'm running next to the main query, which is the one that I'm using to estimate the per batch gradient and update the norm. So these two run side by side, and you need to do privacy composition across both. And you can adapt it on the fly. It's pretty simple. I'm not going to go into the little bits of details of it because they're not that interesting. But the idea of it, if you look at this slide, for a variety of data sets, we've tried it on imaging data sets, we tried it on language data sets, many different models, and it ends up performing almost always same or better than, in hindsight, tuning that clip norm to get the best performance. So if there was a genie that could sweep over all clip norms for every data set and every model architecture and pick, in hindsight, the best clip norm, this approach, this on-the-fly, adaptive, auto-tuned approach ends up either doing just as well or better.
Isn't it the case that we are losing the theoretical guarantees this way? Because we cannot, like, theoretically guarantee that our clipping wouldn't be adjusted to some large part. Or are we also changing the noise ratio?
So the clip, yeah, exactly. So
okay.
The clip norm, when the clip norm changes, the sigma will change such that you still maintain that epsilon per round. So if, let's say, I double the clip norm, I have to double my sigma to get the same epsilon. If I half the clip norm, I have to half my sigma to get the same epsilon.
Okay, thanks.
Yeah. All right, so this ended up being very practical because notice before this method, I had two parameters to set: the sigma and or sigma or epsilon. These two are roughly the same, and the clip norm. Right, so I have two hyperparameters here to kind of set. So when I go to engineers and I tell them, do you want to train with DP? I have to convince them, for what type of choice of epsilon they have to pick, and then what kind of clip norm they have to use. Whereas now I only have one parameter. Clip norm is under the hood, automatically tuned on the fly, and they just have to select the epsilon that they design. There still are, batch sizes and things like that, but let's put that aside. So it's one step towards making this more useful and usable by ML engineers and practitioners who may not be experts on privacy. Okay. All right. So now this is where it gets a little complicated. So we're going to start by doing something interesting. In the context of FL, if you notice what I've done before, I've relied very heavily on the server and adding the noise. And ideally, what we want is we want to give some DP guarantee with respect to the server itself. And then we want that guarantee to get stronger as we move away from the server, because the surface of attack is going to get bigger and bigger. So how many people, for instance, at Google have access to the server that runs the federated learning infrastructure? Maybe tens of people, even less, can actually get their hands on the logs, on the server logs of that thing that orchestrates the computations back and forth between devices. Whereas how many people at Google can request this computation? Those are practically all the teams. So there's like in the thousands of people, engineers, data scientists, people on every single team you can think of, can request those computations. So the surface of the attack gets bigger. And then finally, once we get to deployment, we're talking in the many millions, if not billions of devices on which we're deploying the model. So the surface of attack there is the biggest, so we want the strongest guarantees. That's what we would like to achieve. And therefore, this is now a question that's not just about DP. It's a question that combines many different technologies. So ideally, we want to combine encryption. We want to combine multi-party computation, secure aggregation. We touched on it a little bit. Different flavors of DP. We're going to see those: local DP, central DP, etc. And also a lot of auditing techniques that other speakers like John and Liliana talked about. And we'll touch on this well. So one thing that here we need to use, as we said before, is this amplification via sampling. And while in the data center, I have the data set there, and I could just iterate on it and subsample queries from it, IID. In federated learning, it means I somehow have to uniformly sample from the fleet of devices. This is crucial. If you look at the performance of the unamplified versus the amplified algorithm, there's a big gap between them. Notice here at small epsilons, we're training our next word prediction model. This is an LSD, not a transformer. 5 million parameters, something like that, on the Stack Overflow data set. So if you go to user level DP of 5 or 4 or 3 or 2, as you get closer to those epsilons that we actually really like, you'll see that if we use amplification via sampling, we really can sample clients uniformly at random. We're going to get a much better accuracy. We can get accuracy of 18% or 20% or something like that. Whereas if we don't use amplification via sampling, if we cannot sample those users truly uniformly at random, we get a much weaker accuracy. This is quite crucial, and in practice, we just cannot do it. The reason why we cannot do it is because not everybody is available at all times. Remember from last lecture, we said there's a set of criteria that users need to satisfy. They need to be idle, the phone's recharging, they need to be connected to an unmetered network, so on and so forth. There's a lot of criteria that we need to satisfy. And what ends up happening, if you look at the patterns of how many devices are availability, they end up having this very interesting shape of like diurnal patterns. because at night, the number of devices that are available peaks. A lot of people are sleeping, their phones are connected to Wi-Fi, they're charging, nobody's touching their device. There's so many available devices. And during the day, there's a lot less people that are not using their phones and plugging them to the wall, connected to the Wi-Fi. And so it's very difficult for the server to do anything like uniform sampling. We want the training process to continue. We don't want to slow down the training process, halt some of those rounds. Already, as we said yesterday, FL is slow. We need many days to get that model. We don't want to make it even slower. So it's pretty challenging. So using amplification via sampling in an FL context is just, especially cross-device FL, it's just impossible. So what we are going to see next is a trick to actually achieve that. And so in those 10 minutes that I have before the break, I'm going to switch to the board. And I'm going to start with a little kind of motivation for that. So let's see how we can do it. You can ignore now the slides. And I think this is going to be hopefully. So what I'm going to do is I'm going to give you an example of, like, basically a toy example of something that I want to privatize, and it might not make a lot of sense to you. Like, why is this example even relevant? But I will then show you why this is relevant and how it is relevant. So bear with me. If this example does not make a lot of sense, you will hopefully very soon see why it actually makes a lot of sense in the context of training models. So let's assume you have a model where you have n users. Okay, so let's call them x1, x2, xn.
Yeah, I think people who sit over there may have trouble seeing it because of angle. So maybe those of you who don't see it, just please.
Yeah, if you can't see it, feel free to move.
Feel free to move.
Or you want to sit around. Up to you here. Yeah. Up to you. All right. Okay. So I have these n users, and each user holds a binary value, 0 or 1. Okay. Very simple. Every xi here is a number in 0 or 1. Okay. And the trick here is that you don't have the full data set in one shot. You see it over multiple iterations. So at t equals, let's say 1, you see x1. At t equals 2, you see x2. And then t equals 3, you see x3. So on and so forth. At t equals n, you see xn. Naturally, what I'm doing here is that these are time steps. So if you want to try to map it to ML, every time step is a training round, right? I have n training rounds roughly. But I'm still oversimplifying it, so bear with me, okay? So this is my data set. It does not appear in one shot. I can't access it fully in one shot. I can access it over n steps. I see these things sequentially over n steps. And what I'm doing, the query that I'm trying to compute is called a simple prefix sum. All right, so at t equals 1, I want to compute s1, which is equal to x1. That's the query. At t equals 2, I want to compute s2, which is x1 plus x2. At t equals 3, I want to compute s3, which is x1 plus x2 plus x3. And then at the end of the day, I want to compute Sn, which is, the sum I from 1 to n. My handwriting is terrible. It's okay. All right. All right. So these are called partial sums, right? So this is the first partial sum or first prefix sum, second partial sum, etc. Now, the twist here is that obviously if I could compute the nth partial sum and only release that, it's a simple sum query. And because these are all binary, the sensitivity of this query is 1. It's like a count query as we talked about in this lecture, right? So if the only thing that I wanted to release is this last one, and the adversary is only going to see this last one, I could simply just add noise here, calibrate it to sensitivity 1, and release this Sn, and I'm done. But the point here is I want to release all of them. I want to release S1, S2, S3, up to Sn. So how do I do it? The easiest way of releasing all of them with DP is to add noise to each one of them, right? So one thing I could do is I could take this and compute S1 hat, which is the true S1 plus some noise, right? And how do I set sigma here? The sigma needs to be calibrated to the sensitivity. In the worst case, I don't know which one of these xi will be swapped when I go from D to D prime. It could be the first one, it could be the last one, it could be any one, right? Because I'm going over worst case neighboring pairs. So I need to calibrate to the worst case sensitivity. So I'm going to set sigma squared to be 1, which is the worst case sensitivity for each one of them, divided by epsilon squared. So I can compute here S2 hat, which is F3 plus normal 0 sigma squared, so on and so forth. I can compute Sn, the hat, which is Sn plus normal 0 sigma squared. So notice something here. What's the total amount of noise I would have added to my to all those particle sums? It's n times sigma squared, right? So let's write it here. Total noise is n times sigma squared. And what is the DP guarantee that I can achieve? Each one of them is epsilon differentially private, right? So sigma here is chosen to be 1 by epsilon, because the sensitivity of each one of them is 1. So each one of them is epsilon differentially private, and I computed n of them. So the total epsilon that I have is going to be root n times epsilon. This root n comes from composition. That's what we talked about. If you do n accesses to the query, to the data set, you have to do n compositions, and it's sublinear, and then it's actually rooted. Okay? Now, can we do better? Obviously, if I'm asking the question, the answer is yes. So what should I do? How can I do better?
I think we could use that in all the values at the back.
The values are binary. They don't have to be binary. They can be anything. I'm choosing binary for the sake of simplicity here in terms of sensitivity analysis. They can be vectors. They don't have to be scalars. I want to compute these particle sums with DP in a sequential fashion, in this kind of iterative fashion. Any ideas or tricks I can apply?
We know that S2 is S1 plus another value.
Right.
So we can use S1 hat maybe for decompose.
Okay, we're getting somewhere. There's structure. There's a lot of structure in it. So that's good. There's some sort of a recursive structure. Any other ideas?
If you just add noise to the first one and then compute the later ones from the first one, sort of like you compute sort of S2 hat as like S1 hat plus the.
But the noise is going to add up. I don't want that to happen. Right?
If you just add the noise to the first one and then you do the updates by using the first one.
Kind of close. Okay. I'll maybe accept that. Let me show you the trick, because it actually ends up being very easy. Can I get a new page here? Maybe this one. Plus. Cool. All right, so here's what we're going to do. We're going to build a binary tree. Bear with me for a second. Wide binary tree. The depth of the tree is going to be log n. I have n steps, so log n is the depth of the tree. The number of leaves naturally are going to be n, right? Because if I have a tree of depth log n, I have n leaf nodes. So these are the leaf nodes. So this is here going to be x1, this is going to be x2. And let's assume for the sake of simplicity, because I'm really bad at drawing, we have Let's say 4, but you wouldn't see it with 4. Maybe we can try for 8. Let's assume n equals 8 for the sake of simplicity. So then, now we're going to just do a binary tree. So how am I going to fill this binary tree? This is going to be x1 plus x2, the sum of the children. So this is naturally going to be x3 plus x4. And this is x5 plus x6. And this is x7 plus x8. And again, here I have x5 plus ... x8, the sum of the children. Again, same here, x1 plus ... x4. And then this guy over here is going to be x1 plus x2 ... x8. All right? So notice 2 things. The first thing, what is the first thing? The first thing is that all the partial sums that I want are in this tree. Do you believe me? Sn is here. If I wanted S2, it's here. If I wanted S3, I could just take this node and add to it X3. That's S3. If I wanted S4, I could take this node and add to it this node. This is S4. S5, I would take these 2 nodes, or actually this node, and add to it X5, so on and so forth. So you should believe me that you can get all the partial sums. That's the first thing. So it is a data structure that allows me to get all these prefix sums. The next thing that's very nice about it is that if I change one of these xi's, what happens? How many things change in this tree?
Log n.
Log n, right? Because this x1 appears here, 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 and here. That's the depth of the tree. Same for x2, same for x8, same for x7. Log n times things can change. So this is a data structure. If I go from D to D prime, at most what's going to happen here is that log n things can change. So the sensitivity, if each one of these guys has a sensitivity of 1, the sensitivity of this data structure is going to be bounded by log n. Okay? And it gives me all the prefix sums. And it can give me those prefix sums on the fly, because I don't need to assume I have everything. You know, once I see x1, I can compute s1. Once I see x2, I already have this part of the tree, and I can compute s2. Once I see x3, I already have these here, and I compute s3, so on and so forth. So I can build the tree on the fly. I don't have to build it, pre-hoc or post-hoc. Okay? And it has a sensitivity of log n, which means that I could add noise here, 0 sigma squared, and the sigma would be something like log n by epsilon. Because log n is the sensitivity of the whole thing. Treat it as a vector, flatten it out, and treat it as a vector. The sensitivity of this query, vector query, is log n. So this whole thing is now epsilon differentially private. I don't need to use composition anymore. Because I'm privatizing the whole thing. I may not be privatizing it in one shot, I'm doing it sequentially. But this whole object, if you release it in totality, its sensitivity is log n. And I could compute all the s's that I want. And here's now the interesting observation. When I compute any estimate of any prefix sum, I need to add at most log n nodes. In fact, for the majority of them, it's going to be like either 1 or 2 nodes, right? So if I want Sn, it's just 1 node, that's Sn, the root node. If I want S4, it's going to be 2 nodes added to each other. But in the worst case, I would have to add log n nodes in this tree. So in the worst case, the variance, the noise here is going to be what? Log n times sigma squared. The noise per Si is log n times sigma squared, right? And this sigma is log n epsilon. Now, if you compare this approach to the previous approach, you can see that I was able to improve things from something that grows with n in terms of noise or epsilon, depending on how you want to view it, to something that only grows logarithmically. But this is a very clever trick. And I think I would stop here. But I really want you to absorb this and understand it, because we're going to use this in ML. This simple trick is going to be used to save us from the fact that we cannot sample uniformly at random. We cannot use that amplification via sample. Well, I'll put it together in the next lecture. Just package it. But this is the crux of it.
Only good for cumulative statistics, or
it's good for any time you want to compute continual things. So if you have a streaming application and you're computing queries on the fly, and you don't get to see the whole thing, you see a stream of records or users, this thing kicks in and becomes handy. And this is not the only way. This is the most simple way I can explain the concept, but there's way more advanced data structures.
it's good for like updates from you?
Yes. Yeah, because I can update the model here. I'll talk about this after. So the connection to machine learning and how this feeds into DPML is going to be done in the next lecture. I just want you to understand this basic toy example, and then the connection to ML is going to be done next.
What's the name?
This is called the binary mechanism in the DP literature, or some people call it tree aggregation mechanism. You can search binary mechanism DP or tree aggregation DP, and I can provide you with simple references.
Okay, thank you. Any more questions, Peter? Yuri has a question.
Yeah, it's a great trick, Peter. Just very interesting to observe, because something very similar exists in FHE, and I discussed it in our lectures. It's often used for multiplication, so binary tree for multiplication. So instead of doing the multiplication in a chain, very often we do something like this to minimize the noise growth. And the main motivation there is, instead of using a linear number of levels, you can use log number of levels, and so it's just very interesting to see very similar techniques in both FHE and differential.
Yeah, thanks for the connection. Very nice.